Log on, tune in, find out. Another good idea from Cambridge.
We'll talk about discrete Painlevé equations for recurrence coefficients of orthogonal polynomials.
Okay. First, thanks to the organizers for giving me the opportunity to talk here. Well, my talk certainly has some common points with the previous talk and also with the talk of Nicholas Witte of yesterday. So you might recognize some things. But the main emphasis is that I will actually give quite a few examples of orthogonal polynomials for which the recurrence coefficients satisfy nonlinear recurrence relations themselves, which we identify as discrete Painlevé equations. Okay, the work that I've been doing here is joint work with my student Lise, who is on the back row with a nice pink shirt. Okay. Well, you know now what orthogonal polynomials are. Over here, I will sometimes use the orthonormal polynomials, so with the norm 1 over here. Sometimes I will use monic polynomials, then they come with an hn over there. But of course, it will be obvious from the context which ones I'm using. I'm not always using a weight function over here. This could actually, the integral could be a sum over the integers or over a Q lattice. And these are important when you do with when you want to find Q discrete Painlevé equations. Important thing that you have with orthogonal polynomials is that they always satisfy a 3-term recurrence relation. So my recurrence coefficients are called an and bn, whereas in Alexander's talk they were called rn and qn, but they're the same things. You can, there's a formula for them. You can always express them as these integrals over here, but if you really want to compute them, this is quite useless because it requires the knowledge of the polynomials themselves. So what you really want to do is to have a more straightforward method to compute them. Now, the classical orthogonal polynomials are well known, and we encountered them yesterday in Witte's talk also, and Mizan Rahman also mentioned them. Well, to set the record straight, the Assche table was introduced in 1977 in Oberwolfach, and I have email exchange with Tom Kornwinder and Assche about this. And basically this part over here with the Hahn, dual Hahn, all the way here, was given there by Michael Hoare, where he was talking about his work with Rahman. Assche also gave a talk in that conference on classical orthogonal polynomials without the table, and nobody really got off. And everybody was happy with Michael Hoare's talk with the table. And so that's why Assche wrote the table in his paper with Wilson later on. They missed one case. I think it was continuous dual Hahn. They only had a special case of that. But that was settled by Atakishev and Suslov later on. So this is now the Assche table for Q equals 1. If you I'm missing the arrows because I don't need them right now. But I put these three in color because I will explain some semi-classical extensions of these three. Only the one by Charlier is something that I've been doing. The one with Laguerre and Hermite are well known. Actually, no, the one with Laguerre I also will explain today in the talk. What is typical with these classical orthogonal polynomials, this is what characterizes them, is that there is some weight function that satisfies a first order equation. It doesn't need to be a differential equation with some operator over here. With a polynomial sigma here of degree at most 2 and a polynomial tau here of degree exactly 1. So all classical orthogonal polynomials satisfy this kind of equation. It's called Pearson equation after the statistician Pearson, because the classical weights, Jacobi, Laguerre, Hermite, they are orthogonal polynomials with weight functions that are very typical in probability theory and statistics. These are the so-called exponential weights. But much more is possible. You don't need to use the differential operator. That's just one special case, which gives these three orthogonal polynomials. You can always use the forward difference equation, and then you get some extra polynomials. You can use this complex difference equation. So you take a difference in the complex plane. That will give you the Majkner-Polacek and the continuous Hahn polynomials. You could use divided difference operators, where you actually combine a forward difference with a quadratic function. Or you can use a divided difference operator, where you use this complex difference with a quadratic function, and you get all these. And so the whole ASCII table is based on this simple observation over here. You just need, and the classical case is when the degree is at most 2, and the degree is 1. A consequence of that Pearson equation and some simple methods of integration by parts or something like that is that you can actually have some formula for the derivative or the difference of the orthogonal polynomial times sigma. It can be expressed as a finite sum of previous polynomials. And in a way, this equation is one part of the lax pair. So it's like a backward operation, whereas the recurrence relation is the other part of the lax pair. It's the Jacobi matrix. So you really have the lax representation here by combining this relation and that relation. This is sometimes called the structure relation, and this is, of course, the recurrence relation. And if you write out what the compatibility is between this equation and that equation, then you get some information about the recurrence coefficients and these coefficients over here. If you do that for the classical orthogonal polynomials, with sigma of degree at most 2 and tau of degree 1, then these compatibility relations just give linear equations for the recurrence coefficients, which was the first example that Alexander was giving there for the Hermite polynomials. And you can solve these linear equations, and you can get all the recurrence coefficients in the ASCII table straightforwardly. Some of them require a bit more work, but basically there is nothing very difficult with it. And you can extend this whole idea also with some Q operators. You can, for instance, use this Q difference operator over here. Or you can use a divided difference operator, but not with the quadratic function here, but with this quadratic in the Q to the power x. And if you take lambda, the gamma here equal to 0, then this divided difference is actually similar or equivalent to this ordinary Q difference operator. Or you can use the most general operator, which is this ASCII-Wilson operator. It applies to functions defined on the interval -1 + 1. If you map that function to the unit circle like this, and then apply this symmetric Q difference operator, then you get the ASCII-Wilson operator. You could also combine, instead of using forward difference, you could use that symmetric difference also applied to this more complicated function. And you get a much bigger set of polynomials, which are still called Q classical. It's the Q ASCII tableau, which has been set up by Kuckuck and Swartau. You can find it online on the web, or you can find it on the archive. It's a much bigger table. It has a left part and a right part. So this is the left part, which starts with the ASCII-Wilson. And basically, these are all the continuous ones. And I will be describing these three semi-classical extensions of those in my talk. And there is also a right part, which has on top the Q-Raka polynomials. And basically, these has all discrete orthogonal polynomials. There's one here, the big Q Jacobi, which is both in the left and in the right. So it's somewhat in the middle of the ASCII-Wilson and the Q-Raka. And I will also describe these discrete Q-Hermite polynomials, well, a semi-classical extension of that. So what are semi-classical weights? Well, again, we start from the Pearson equation, this one over here. D is one of the operators that I already mentioned earlier. But now we do not require the conditions for the classical weight. So sigma may be of degree greater than 2, or tau may be of degree different from 1. You still have such a relation over here. You can express that difference of that polynomial times that sigma polynomial as a finite sum of previous polynomials. But now the number of terms is higher. It actually goes from n minus s to r. R is the degree of sigma, which is already greater than 2. And there's also this s coming in over here, which is the maximum of the degree of sigma minus 1 and the degree of tau. So s is sometimes known as the type of the differential equation. So you get more coefficients here that you have to determine, but they are somewhat connected because at the zeros of sigma, you know that the right-hand side has to be 0, so there are some connections between these coefficients. As a matter of fact, these ANs are not the most useful coefficients that you need to determine. There are some which are somewhat more useful to use, but in that case you will not be using that relation over here, but something which is equivalent, which is called the Q-ladder operation, or ladder operations, or Q-ladder operations. If you now express compatibility between this structure relation and the 3-term recurrence relation, well, you have more equations now. So you will also have higher order recurrence relations for the recurrence coefficients an and bn, and also for these coefficients which come out of this whole analysis. So it's not first order anymore, it will be second order or higher, and they're always nonlinear recurrence relations. And the thing that we set up to do is, well, we try to find some classical, semi-classical weights, some special sigma, tau, some operators d, and try to find out when these recurrence relations over here are of second order. And if they are of second order, we can check, for instance, singularity confinement, so that there is some hope that they're Painlevé equations. And if they indeed satisfy some singularity confinement, the second aim is to try to identify them with some discrete Painlevé equation. It's some trial and error, and we're not the only ones doing that. It's some business now, and I'm trying to please members of the audience here by putting on this slide. So Nicholas Witte already yesterday, he explained this whole method of working it out, and he really starts from the top, from the Assche-Wilson level. If you really want to find the lower ones, then you need to take, then you need the arrows. Pardon, Paul, Tom. If you want to go down, you need the arrows. We prefer to start from the bottom and to work up, because at the bottom it's somewhat easier to identify the discrete Painlevé equations, and then we hope to find some structure in the table. As Alexander also mentioned, well, the first nonlinear recurrence relation that really was worked out was done by Schohat and probably even by Laguerre, but we can't really find the equation in his work. But that was in the 30s, and Freud did it in the late 70s. But they got the relations, and people tried to solve these recurrence relations, failed to solve the recurrence relations. And I really believe that Itz and his co-workers are the first to recognize them as discrete Painlevé equations. Perrival and Shevitz, for instance, they also found discrete Painlevé equations, but they were working with orthogonal polynomials on the unit circle, which I will mention in a minute, and they also recognized them as discrete Painlevé equations. Magnus from my sister university, Leuven in Belgium, he also picked up very quickly that all these Freud equations are Painlevé equations. He found some relations between the discrete and the continuous Painlevé, and he set up a whole he found a whole setup to work out more of those. And he did, for instance, generalized Jacobi and several other ones. Chairman, it's always nice to please the chairman. You get some extra minutes. And Stewart and Spicer, they also did some semi-classical weights, getting out the discrete Painlevé equations. And then Chen and Ismail, they also have worked out quite a few examples. And I hope I have not insulted anybody by forgetting them. Add to the list, okay? Okay, so this is historically. If I put names there, these are the people that you have to praise in that case, Schohat and Freud. It's this weight over here, a special case of in this family. You can actually put in an extra singularity over there. One of the recurrence coefficients is 0 by symmetry, and the other recurrence coefficient, the an, satisfies this simple equation. Okay, and if I use this delta n over here, it means it's 0 when n is even, and it's 1 if n is odd. And that was worked on for a long time in the late 70s, early 80s, called Freud's equation. People didn't really get too much out of it. They got the asymptotics of the recurrence coefficients out of it. They also found that the ones that you need for your orthogonal polynomials is a special solution which remains positive. It's the solution which starts with a0 is 0 and remains positive for all n. And then it was recognized that it's really a particular case of this discrete Painlevé 1 equation. Okay. One that I did with a colleague from Cameroon, Foupo-Agnini, is Charlier. And this is already one where you're not working on the real, it's not a continuous orthogonal polynomial. So you wouldn't be able to use the Riemann-Hilbert problem just as Alexander Hicks was explaining it here, but you can use a modification. You use the same matrix and it solves a problem but for meromorphic functions, not for functions with a jump. The Charlier is here with when the 2 is replaced by 1, you get Charlier polynomials. But when you put the 2 over here, you get a semi-classical polynomial. Orthogonality is on the integers now. I'm summing over the integers. And with this transformation, instead of looking for the an, you really are looking for the cn. And the bn can then be expressed in terms of cn. Well, the cn's then are given by this nonlinear recurrence relation. And we were able to identify this as discrete Painlevé 2. It's this one over here. And in this case, you can also get the asymptotics. The Cn will now tend to 0, and very fast. Well, discrete Painlevé 2 also appeared in that work of the physicists Perival and Shevitz, but they were working on the unit circle. So the orthogonality is now given by this Hermitian orthogonality, a weight function over here, which is actually this exponential of lambda times the cosine theta. There is no 3-term recurrence relation, but there is something even more interesting maybe. The Phi are the monic orthogonal polynomials. These are the orthonormal. If I put capital Phi, then they're the monic polynomials. They can be obtained from this recurrence relation where these alpha n are nowadays known as Verblunski coefficients, thanks to the work of Simon and his book. And these Verblunski coefficients, for this weight, they also satisfy this discrete Painlevé 2 equation. In a way, orthogonal polynomials on the unit circle are maybe somewhat more natural because you only need to find one sequence over here. Only these Verblunski coefficients are necessary. Whereas for orthogonal polynomials, you always have 2 sequences, the ANs and the BNs, and it's a bit complicated to set them up in the right way so you get the right equation. For the Verblunski coefficients, you just need to find these ones. Okay. Now let's go to some Q discrete polynomials, and this is where we get in again. Q discrete Hermite 1 polynomials. I mentioned those on the right-hand side of the Q ASCII table. They are orthogonal -1 + 1 with a weight which is given by such an infinite product over here. But the integral is now not a continuous integral, it's a Q integral. And a Q integral is just the sum over powers of Q. Okay? Also in this case, basically you cannot set up the Riemann-Hilbert thing like it was, but you can still do it with a meromorphic function with a punctured plane, 0 removed. Okay. For the Q discrete Hermite polynomials, if you do the compatibility, you just find a linear relation, and the recurrence coefficients an turn out to be these simple expressions in Q. Q is between 0 and 1, so this goes to 0 exponentially fast, and if you blow it up by Q to the power n, it goes to 1. Or Q to the power n minus 1, it goes to 1. Again, by symmetry, there are no bn's, so you don't need to determine them. You have to think of this Q exponential of this Q Pochhammer or this Q rising factorial as the Q Hermite function. Sorry, the Q exponential function. There are actually two Q exponential functions. This is one way, and it's actually in the limit. It goes like it behaves like e to the power minus x squared. So that's the Hermite weight. So if you really want to do something like the Freud weight with e to the power minus x4, you replace x squared everywhere by x4. So this is what we feel was a good Q discrete Freud polynomial. Actually, I didn't come up with it. Frank Nehef came up with it. And if you work around and do the compatibility, if you write the an squared like q to the power n minus 1 yn with yn the unknowns, then the yn turn out to satisfy this nonlinear equation. Okay? We couldn't really identify this one, and we decided to try another Q deformation. We take this Q exponential with another Q exponential with a parameter in it. If you let C tend, if C is minus 1, it's the other one. But this has a little bit more flexibility with the C, and you also get some nice relation over here. And since this is like a Q extension of the Freud weight, and the Freud weight gives discrete Painlevé 1, we were thinking of calling this Q discrete Painlevé 1. But then my student, I have two students actually, Lise and Christophe, they decided to put in one more parameter. Let's see. They put in x to the power alpha over here. So you get this alpha parameter. They worked out the recurrence relation there. And then you see something behaving when n is even and when it's odd, you get some different right-hand sides. So they thought it would be more interesting to bring in new variables, un, which are the even ones, and vn, which are the odd ones. And then you get a system of equations. And then you look into the lists. There are some lists available nowadays. Peter Clarkson once compiled a list, which I took over in a survey that I wrote. But a more comprehensive list is in Grammaticas and Ramani. They have written a review. And indeed, you can find that one, well, as a limiting case of this system of equations. And it's important that the product of these four zeros is 1. That gives the integrability. And indeed, if you take this, and it's called asymmetric Q Painlevé 5, or in Sakai's classification, it corresponds to E6Q. If you take the parameters like I've written over here with a free parameter kappa, so if I take S kappa over here, I put the kappa over here, there's another kappa over here in the A, and then let kappa tend to 0, you get this one. So it's a special case, it's a limiting case of Q Painlevé 5, asymmetric Q Painlevé 5. And this is about the highest we got so far, asymmetric Q Painlevé 5 or E6Q. Yep?
But you're taking a limit, so it's not actually in that case.
it should be a lower level, but I couldn't identify it with one of the lower levels. And so probably it's there, but we have to find the right transformation. But, okay. Semi-classical weight. Well, so we get interesting Painlevé equations if you go from Hermite to Freud, e to the power minus x4. So we decided, why not go from Laguerre and take a quadratic transformation. Laguerre is e to the power minus x. Well, why not take here just a polynomial of degree 2? And then people tell you, yeah, but that's related to the e to the power minus x4. Okay, we know that, but let's just work from that one, but on 0 infinity. In the Riemann-Hilbert problem, you have to put in an extra condition near 0 because that's an endpoint of the curve. But it doesn't really give too much problem. One thing that changes is that the Bn is not 0 anymore. The Bn are going to be positive numbers, and the An are also to be determined. Well, the Pearson equation in that case, it comes with a sigma polynomial of degree 1, just x, and it comes with a tau polynomial of degree 2. And there are two parameters, the parameter t over here and a parameter alpha over here. So this is the most general polynomial of degree 2 up to 1 scaling. Okay? And if you do the compatibility between recurrence relation and structure relation, you find that if I call the an after this transformation yn, and if I call the bn after this transformation xn, you come up with this system of equations for the xn and the yn. And this is, let's see, asymmetric Painlevé 4. Okay? And that's interesting. So we now found some discrete Painlevé equations for this generalized Laguerre. And then you remember what people said. Well, this is related to Painlevé 4, to the Freud weight, just by quadratic transformation. And indeed, we know that. So if you do the quadratic transformation, you can relate the recurrence coefficients of this Laguerre with the recurrence coefficients of Hermite, for which you know Q Painlevé 1 is existing. And that relation is really a Miura transformation between this asymmetric Painlevé 4 and discrete Painlevé 1. Again, it's not really asymmetric Painlevé 4 because you have to put in some limiting case. Oh, sorry. You really need to put in some epsilon over here, and then let epsilon tend to 0 to retrieve this one. So it's really a level lower, but I can't identify it then again. But maybe you have to stare at it a little bit longer. Okay, so this is the symmetrization that I was telling about. If you really work on the minus infinity plus infinity and replace x everywhere by x squared, then you would get that weight. I already handled that. That's the Freud weight, which was already considered by Shohat, which satisfies this discrete Painlevé 1 equation. I put in the t now, that just this shift t that comes in there. The general theory of orthogonal polynomials, which you can find in Chihara's book, relates the recurrence coefficients of Laguerre with the recurrence coefficients of Hermite. So you have these relations. You know that these satisfy discrete Painlevé 1, and we know that these satisfy asymmetric Painlevé 4. So that is the Miura transformation between these two. So orthogonal polynomials gives you more than just the discrete Painlevés. It gives you some natural transformation, quadratic transformations. The same weight, e to the power x squared tx, can be used, but now we can put in some asymmetric weight on the real line. If I put that Laguerre weight on the positive real line and on the negative real line, but with a little change here in that constant over here, then it's not symmetric anymore, so you will be putting in bn's. You will get exactly the same Painlevé equations. And the only place where it differs is in the initial condition. So the initial conditions are y0 has to be minus alpha over 2, and x0 has to be in terms of the first moment of this weight, and that first moment will contain the ratios C1 and C2. So you get a whole family of solutions of this discrete Painlevé 1 depending on the ratios C1 and C2. And in that family, they form an interval. If you choose your initial condition in that interval, the solution of that discrete Painlevé equation will never hit a singularity. And the case where C2 is 0 gives me the Laguerre that we had before. The case C1 is 0 gives the same Laguerre but with a minus sign. Okay? And those are actually important because those are again limiting cases. There is a unique solution of this discrete Painlevé satisfying a positivity constraint, and that fixes the initial conditions. But it's not anymore unique for these weights because there you need that initial condition precisely. Generalized Hermite polynomials are the polynomials that come from here, e to the power minus x squared, x to the power alpha. Usually the Hermite polynomials are the ones with alpha 0, but Chihara, for instance, studied these generalized Hermite. They fall into that class over here by taking C1 and C2 equal to each other. If C1 and C2 are equal, you would get these. And then all the bn's become 0, and your Painlevé equation actually linearizes. It boils down to this one and to this one, and you have to take signs over here. So the solution of that one really gives explicit formula for the recurrence coefficients of generalized Hermite, which you can find in Chihara's PhD. Chihara wrote his PhD on exactly these generalized Hermite. So you don't always you don't always get Painlevé. Sometimes it linearizes, but these are exceptional. Another special case is when I take t equal to 0, this one, then the system of Painlevé equations really reduces to only one equation. And this is one that we can identify readily. It's discrete Painlevé 4. You see, you do get quite some equations over here, and then people ask me, why are you looking for all these Painlevé equations? Well, if you have this equation, and this is an equation, a weight that appears into physics, it's a Rayleigh, I guess. You really need it, not a minus infinity plus infinity, but really on 0 infinity. And you really need to get the coefficients, the recurrence coefficients. Well, you can't get them precisely. The best you can do is to get this Painlevé, which is nonlinear. But the fact that it's Painlevé means it's not hopeless. It's really on the boundary between linearizable and non-integrable. And for instance, if you really want to work out how the yn depends on the first initial conditions, the complexity doesn't grow too fast. And this algebraic entropy gives a handle on this. It's still in control. So Painlevé means you're in control. It's not hopeless. But on the other hand, it's not the right way to do it numerically, because the equation is usually numerically unstable. But you can solve the discrete Painlevé by looking for a fixed point of that equation, and that's quite stable. Okay, let's go to Q Laguerre. Q Laguerre is this weight over here on 0 infinity. It's another extension of the Laguerre polynomials. Again, remember that this really replaces it's a Q extension of the exponential function. Putting it in the bottom gives e to the power minus x. Okay? It's a weight with infinitely many poles on the left-hand side of the real line. So not here, but on the left-hand side. And it's an indeterminate weight. So this is just one. There are other weights with the same moments. The orthogonality is just plain integration. Even though it's Q, it's just plain integration. Turns out that for this weight, you can find the linear recurrences for the recurrence coefficients, and they're reasonably handleable. But the an now grows exponentially fast with Q, if Q is between 0 and 1. And the Bn also, something's missing. That should be the exponent of q. Also the q grows exponentially fast as 1 over q to the power 2n. So again, we do the same trick. We replace x by x squared to get some semi-classical extension. And with this transformation over here, instead of looking at an, I'm looking at this simple function of an. I call that xn. You get this equation over here. And then you look into your table, see what happens. It's actually a QRT. You have this one as a function of xn, and it's a special case of Q Painlevé 5. Special case because usually you have 4 different roots, but 2 of the roots always are the same here. And you only need to solve this equation over here that gives the xn. Once you have the xn's, the bn's follow from that by taking the positive root of that equation. So we're really building up a whole list of Painlevé equations. Q Painlevé 5 is nice. We also had asymmetric Q Painlevé 5, which is a level higher. Let's see what else we can get. Well, let's symmetrize again. If you symmetrize, then you would get this weight on minus infinity plus infinity. Well, turned out that Ismail and Mansour, a student, already were studying this Q Freud weight. So we had a look at their paper, and they seem to find a Q discrete Painlevé 34. Whereas we would expect from the coalescence of Q Painlevé 5 to find a Q Painlevé 3. So we think we're going to look a little bit more into detail. They only handled the case where this power is not available. So it could be that by putting in the alpha, you actually get Q Painlevé 3. But 34 came up in the previous talk. That was discrete. Here, Ismail and Mansour claim to have found a Q discrete Painlevé 34. Little q Laguerre, it's a similar weight, but instead of having such a Q Pochhammer in the denominator, you put it in the numerator. Okay? Now it has infinitely many zeros on the positive real line. The orthogonality now is on 0, 1, but now with a q integral, dq. So it's a discrete orthogonality. For the classical orthogonal polynomials, this little q Laguerre is basically the same as the other q Laguerre, but with q replaced by 1 over q. So with the q Laguerre that I had before, in order to get orthogonality, q has to be between 0 and 1. If you let q be greater than 1, you don't get orthogonality on 0 infinity, but you do get orthogonality on 0, 1, but discrete. And basically it boils down to integrating along all the poles and do some contour integration to see that this is the correct integrability. Not surprisingly, if you work out the compatibility, you get the same Q discrete Painlevé 5, and the only difference is that Q is replaced by 1 over Q. Okay? So you get both cases, Q between 0 and 1 and Q greater than 1 by combining Q Laguerre and little q Laguerre. So let's move on.
There is a special case. It's a special case.
Yeah, it's still the special case where you need to take. No, let's see. No, there's no special case here. Well, it's you have double roots. Yeah, that's the only. Yeah. The general Q discrete Painlevé 5 would have 4 different roots, but this has double roots.
But the moment problem is here is not.
For this one, the moment problem.
Right?
For this one, it's determined. For this one, it's determined.
No, but I mean, in other cases, you never mentioned that when
this one is
it's
indeterminate
and when it's not.
This
What
is
I'm
undeterminate.
saying that actually in those cases, when it's not determined, you can construct other examples. Is that correct understanding?
But you can get other weights, but you get the same recurrence coefficients. The polynomials
Oh.
remain the same.
So, okay, so result will be the same.
Yeah.
And
The
that will be
recurrence
the-
coefficient, you can get other weights, and surprisingly, the weights satisfy the same Q difference equation.
No, this
Okay.
is the limiting circle. So you
Sorry?
the limiting circle. So you have your potential in different situation. It has several spectral functions.
For instance, for this one, the Q Laguerre, I used the orthogonality here on 0 infinity, but a continuous orthogonality. You can actually find discrete orthogonality on powers of Q. Okay? But since the moments are the same, the polynomials are going to be the same, and therefore also the recurrence coefficients. Okay. The last example, still disfigured, since indeterminate moment problems, the typical indeterminate moment problem is still disfigured. Usually, if you look in Sego or if you read Stiltje's paper, Stiltjes-Wiggert comes with a log normal distribution, which is this one. And if you put in the parameter gamma over here, you can actually find the recurrence coefficients exactly, because that's a classical weight. It's in the left-hand side of the Q ASCII table. It comes in as powers of Q. If you define Q to be the exponential of -1 over 2 gamma squared. So the gamma and the Q are related this way, and the Q is between 0 and 1. Okay? It's indeterminate, and you can see it from the recurrence coefficient. The recurrence coefficients go very fast. If Q is between 0 and 1, it really grows like Q to the power -4n. And the Bn grow like -2n. There are many weights available. You don't really have to take this log normal weight. This is also a weight for the Stiltjes-Wiggert polynomials. It has this product of two Q Pochhammers, and it's a very peculiar problem. It product. It has -x here and -q over x here. And actually, this is a Jacobi theta function. You can see that by using the Jacobi triple product identity. If you multiply by one more product, like QQ, you can write it as an infinite sum, and that's the Jacobi theta function. So this, if alpha is equal to 1/2, this one has the same moments as that one. And this one is a little bit easier to handle in many cases. It satisfies a Pearson type equation. Both actually satisfy the Pearson type equation with degree of sigma less than 2 and degree of tau equal to 1. And you can, from that, compute these recurrence coefficients exactly. But this is the weight that we're going to extend to a semi-classical weight. This is the one which is a little bit easier to handle. So instead of x's, I'm putting x squares everywhere. By the way, I'm also putting q squares everywhere. That makes just life a little bit easier. And then it turns out again, you don't really look for an equation for the recurrence coefficients. They are not the easiest one. You scale them, just a affine scaling. You subtract this power and you multiply by this over here. Then the xn's are actually bounded and satisfy this equation. And that, just look in Grammaticus and Ramani, it's Q discrete Painlevé 3.
In with the doubling of the roots.
With the doubling in the roots, yeah. If you don't want the double roots, you need to get different extensions. Instead of taking this, it's probably better to take in two factors. We haven't done that yet, but we're working on it. And let's see, one more extension, which is called generalized Stiltjes-Wiggert, is this one. You even put in this q factorial in the top. This is really what Chihara calls generalized Stiltjes-Wiggert. And the p, if you take p equal to 0, you get the previous one. If you put p equal to q, this and this cancel, you get Q Laguerre. Okay? So Q Laguerre in a way is a generalized Tiltes-Wigert. This one you can also get the recurrence coefficient explicitly because this is classical. But the semi-classical variation is to put it like this. You would now get this, it's Q discrete Painlevé 5, and the other one is just a symmetric way. Once you have xn, you can compute pn from this as the positive root. So we haven't really finished everything. We're only at the bottom 2 levels of the ASCII table, but there is already so much variation, and there are many ways of making a semi-classical variation. And quite often you find Painlevés. Q discrete Painlevé 5, 4, 3, 2, 1. So next is, well, basically we've done the simple ones with the differential operator and the simple ones with the Q difference operator. What we really need to do now is to move up to the operator with the complex difference or with the divided differences. But I'll probably tell about that in another 2 years, or when Lise has finished her PhD. Thank you. So.
Question is, so in most cases, the discrete Painlevé equation arising in your construction, it's a very special case or limiting case.
Yeah,
and
because we're still on the
yes,
on the
yes.
bottom level.
So
Yeah.
my question is it possible to introduce some parameters in your construction, somewhere in your construction, to get more generic discrete Painlevé equation? Is it possible?
I think we need to go higher up, or in this case, a possibility would be. Okay. So I've put in the bottom. I'll put x to the power alpha. Instead of putting in a quadratic factor like over there, I put in just two factors over here, and then the C may actually move the 2 zeros apart, and then you would get 4 different zeros, and a similar one here for the other factor where the x is in the bottom.
So then, what is the corresponding orthogonal polynomial?
It's some generalized Stieltjes Hermite, but it's not explicitly known. Even since the recurrence coefficients are not explicitly known, I very much suspect that we really can't find simple expressions for these polynomials. But, although all the classical ones can be expressed as hypergeometric or basic hypergeometric ones, I think these ones cannot be expressed in that way, unless you hide the recurrence coefficients in there. But, okay. Tom?
With these semi-classical weights, the structure equation gives certain expansion coefficients. So they are always explicitly known.
Yeah, they also come out from the analysis. They're in terms of the recurrence coefficients again. Yeah.
But you said your nonlinear equation you get by the compatibility
Yeah.
of the two-term recurrence relation and the structure relation.
Yeah. Yeah.
But
You eliminate.
But you end with the equation only involving the coefficients.
Because that's the one I'm mostly interested
So,
in. Yeah. But for instance, when you have the compatibility, then what you do is you eliminate these coefficients and you get recreations for the an and the bn. Yeah.
Oh, you can eliminate.
Yeah.
So they are not always.
Well, if you look out how the elimination goes, you have a formula. But in terms of the recurrence coefficients, so they're not explicit. Some of them are explicit. Usually the leading one is sometimes n, because you just have to compare coefficients. And the last one often is like a product of the recurrence coefficients. Actually, you can recognize them. So usually they're like products or sums or squares.
So it is not like in continuous case when you, at least in this case, when you can always express all this coefficient A capital A in terms of recurrence coefficient.
You can always express them in terms of the recurrence coefficients, but it's a nonlinear expression in the recurrence coefficients.
No.
But they're not explicit, they're in terms of the recurrence coefficients. Yeah. It's explicit enough.
no,
It's not like it's a rational function of n. It's some rational function of the recurrence coefficients.
Yeah. But then you have arrived at your nonlinear equation, and either it is somewhere in this big classification of Painlevé, discrete Painlevé, and so on, or not. And now, if it's not, why is it not interesting? You have already answered it, because then it's hopeless to solve. But even equations that are hopeless to solve may be interesting.
Yeah, my belief is that there will always be integrable. So I don't really, well, the way you set them up, they come from the whole scheme. They do satisfy these lax relations. So, but they may not be identifiable as Painlevé. They may be higher order, for instance. The list only contains second order Painlevé. So. But I think when we were looking for the Meixner polynomials, we found a third order equation. It's still interesting, of course.
You always can do asymptotic analysis in your work, and also there is this big almost book by Miller, McLaughlin, and yes, and Bake, when they do a lot of asymptotic analysis for.
Yeah. Sure.
Well, they probably don't call it discrete Painlevé equation, but they do asymptotic analysis for recurrence coefficient of polynomials with discrete weights.
Yeah. Still. But what I didn't do also is you can also take derivatives with respect to some of the parameters, and you could also get the Painlevé, the continuous Painlevé out of it. So, but that's been done over here. And
Can I ask, are there any cases where there's scope of finding higher degree, higher order, higher degree?
higher degree. Let me see. So far, not. No.
Or is it
But,
impossible from
No, actually, when you take e to the power 6, you would already get.
In continuous case,
Yeah, you get the whole the whole hierarchy of discrete Painlevé 1.
Yeah,
And probably over here, I always took like replace x to x squared. I can replace x to x cubed, and I get higher degree polynomials. And I would call that the whole hierarchy of that Painlevé, but I'm not sure whether they are the hierarchy. But probably they are, because you're just.
no, this I didn't mean. This is order. I mean higher degree,
Degree.
meaning higher order.
Yeah, you
in the
mean
derivative.
instead of whatever. Yeah, okay. I didn't get those yet.
What kind of correspondences? Integral correspondence. There are some examples.
Yeah. No, it's true. It's degree and order. Yeah.
No more questions. Thank you all.